For a quiz problem, we had a ladder or a beam 10 feet long, resting at a point 6 feet from a wall, resting up against the wall with a base at a point 6 feet from the wall. We were asked to sketch all the forces acting on this ladder or beam or whatever it is. Before we do that, we work out the geometry of the situation. We note that by the Pythagorean theorem that the height of the top of the ladder along the wall is 8 feet. So we have all three sides of the triangle, and the inverse tangent of the height over the x here is 53 degrees. So we'll just keep those things in mind and proceed to look at the forces. Okay. The first force on the ladder, we assume it's a uniform ladder or uniform beam, acts at the center of mass, and it's just the weight of the beam. So the weight acts at a point 5 feet from this end, 5 feet from this end, straight down. That causes a torque about this point. Causes the ladder to want to rotate around this point. The only thing we have out here touching the ladder is the wall, so the wall is stuck with having to exert enough force to overcome the rotational tendency of this weight. In other words, whatever force the wall exerts, it has to result in a torque that's equal and opposite to that of this weight. Now, another provision was that there is friction along the floor, but there's no friction on the wall. So the wall can only push this way with a normal force. And we call this the normal force of the wall on the beam. Call this ladder a beam. Okay, normal force of the wall on the beam, it's in this direction. Now what do we have down at this end? Well, we can have a normal force exerted by the floor, and we can have a frictional force exerted by the contact between the ladder and the floor, or the beam and the floor. The normal force we'll call the normal force of the floor on the beam, and that's got to be perpendicular to the floor because that's what normal forces are. And then we have a frictional force parallel to the floor, which we kind of assume is in this direction. We'll see that in a minute. We can make a couple of observations. The only two forces we have in the x direction are this normal force and the frictional force, so they're going to be equal. The only two forces we have in the vertical direction are the weight and this normal force, so these two are going to be equal. There aren't any other forces acting here. The only forces can occur due to gravity, we've got that, or due to something that happens at the point of contact, which is normal force. Here it's normal force and frictional force. Remember, there's no frictional force up here. Smooth wall, polished, greased, whatever. So we conclude that the magnitude of the normal force of the floor and the beam is equal to the weight, magnitude of the weight, and the magnitude of the normal force of the wall on the beam is equal to the magnitude of the frictional force. So now we have this picture where we've taken the weight force and broken it into its components, mg cosine 53 degrees and mg sine 53 degrees. And I think I probably got those backwards. Yeah, I do have those. That should be sine, that should be cosine. So, let's make a note of that. We have a sine there, we have a cosine there. Obviously, when this angle is 0, all the weight's going to be down, and if it's mg sine of the angle, we're going to have a 0 force acting down, so that doesn't make any sense at all. From these forces, we can determine the torque of the ladder about either this point or this point. We're going to choose to determine the torque about this point because we have only one force up here, to supply the counter torque. And remember that we see that the wall, normal force of the wall on the beam is a result of the attempt of the beam to, or the effect of the weight of the beam in producing a torque in this direction. So we're going to use rotation about this point to determine this force. And we do that fairly easily. The sum of the torques is the moment arm of the mg cosine 53 degrees times the moment arm, which is 5 feet, and then the 8-foot moment arm of the normal force. Now let's look back just a minute and see where we get that 8 feet. We're using the perpendicular component in the 5 feet to get the first force. We're using the normal force and the 8-foot distance between the point of rotation, or the axis of rotation, and the line of this force in determining the torque due to this force. In any case, we get this equation, so we quickly solve for the normal force of the wall on the board, or the beam, and we get 0.375 mg. Combining that with our condition for x equilibrium, which, as we saw before, tells us that the force minus the normal force of the wall on the beam is 0. Frictional force is the normal force of the wall on the beam, and similarly the normal force of the floor and the beam is equal to the weight, or mg. So now we have all the forces acting on the beam.